on for, I guess, 5 seconds.
All right, welcome everyone to the last theory seminar of this semester and year.
I guess.
Sorry?
No, it was the YouTube thing. So, yeah, go ahead.
So it's a pleasure to have Seth give the theory seminar today. A lot of you have already met Seth because he was here for, I guess, almost a month earlier this semester. So Seth is a graduate student at MIT working with spinful, and so he's going to tell us about some of his recent work today. So Seth, the floor is all yours now.
All right, thank you, Devanshan. Yeah, so since you guys were kind enough to let me postpone, I will be talking about work that's already on archive. I'll have the number here if you have questions and you want to look up more detailed reference. That's the paper to go to. And I did this work with Senthil and Devanshan. So thanks to both of them. It wouldn't have been possible without them. But today I'm going to be talking to you about a theory of a continuous bandwidth tuned Wigner-Mott transition. And I will go through and I'll explain, everything that's going on here as we go through the talk. So just to give you a kind of an idea of what I want to convey, the biggest thing that I want to get across is that adding translational symmetry breaking to a metal insulator transition is very hard. And it's likely to spoil some common metal insulator transitions. So that will provide our theoretical motivation. And then I'll briefly give sort of a hint of experimental motivation before getting into the meat of the theory. So please feel free to interrupt me at that time or really at any time with questions. And I'll try to clarify whatever it is that I'm saying. And finally, I'll close out with some predictions for experiment. Hopefully, some of your colleagues will be able to see some of the things that we're suggesting in the near future. So let's just jump right into the theory motivation. So I'll introduce the simplest possible metal insulator transition at half electron filling. So just as a convention here, I'm going to use nu C for electron filling factor. Nu B is twice nu C because of spin, and this will be the charge filling factor. If you read the experimental literature, often the charge filling factor is what's used. Great, so one other thing is that all of my cartoons that I'll be showing will be on the triangular lattice, even though most of what I'm saying is more general than just the triangular lattice. But so with this metal insulator transition at half filling, what needs to happen? Well, you need to have a disappearance of the entire Fermi surface. So on the metallic side, you have just a ton of low energy degrees of freedom, all of these electrons, and they all need to disappear as you go into the Mott insulator. And at that critical point, you develop a charge gap, which will have some scaling, some critical exponent at this quantum critical point. So you can ask, how do you do this abruptly? And one idea which was expanded on by Senthil, and I'll give a lot more detail about this, but just to give the kind of basics of the idea, you split the electron at this metal insulator transition. Your electron, you treat it as having some charge degree of freedom. B is this charge-on or boson, will have charge E, and F will be the spin degree of freedom, the spin-on, that will be a fermion. And when you do this, you can sort of picture what's going on here as you tune through this bandwidth tune transition. You'll have a metal with your standard Fermi surface. And then on the Mott insulating side, you freeze your charge degrees of freedom, your charge-ons, one for every lattice site. So here you can see what that looks like in real space, but you don't freeze out the spinons. So the spinons still have a Fermi surface. But if you try to move charge through this system, it's not going to work because all of your charge degrees of freedom are frozen. And so you might think, and it turns out to be the case, that this is kind of described by the charge degrees of freedom having a superfluid Mott transition across this critical point. And the spin degrees are really just kind of spectators. And we'll see that when you're careful, this is actually true. But this is all at 1/2. You know, what happens at fractional fillings? What fractional fillings in real space, you can see we're no longer going to have a charge on for every lattice site. Instead, we have some gaps here. And what those gaps mean is that we no longer have translational symmetry in this Mott insulating state. So if I start here and I translate, it's obviously going to be different. And so I've broken translational symmetry. So not only am I going to get a charge gap if I want this to be an insulator, but I'm going to have the appearance of some kind of charge order parameter. So for the particular charge density wave that I'm showing here, this is a √3 by √3 order parameter. And that's going to have some generically different critical exponent at the quantum critical point. But there's a much deeper problem, which is that actually this charge density wave order parameter can couple to the spin-on Fermi surface. So what I've drawn here in this schematic, I drew the charge degrees of freedom coming from the same critical point that the charge density wave came from. So we're breaking translational symmetry at the same time that we're becoming an electrical insulator. But that may not be true, right? If we take into account this coupling here, we may sort of spoil both of these orders from appearing on the insulating side. So what do we do about that? That's kind of our motivation. So just as an aside, one way that you could try to think about a metal insulator transition at these fractional fillings is a kind of a weak coupling analysis. But we don't do that. I will just summarize it here because it's a popular approach in some of the literature. So one thing we could do is we can take this electron Fermi surface at 1/6 filling in the electrons, and we can couple it to this charge density wave. So that will reconstruct, once we start to get a non-zero charge density wave order parameter at this critical point, that will reconstruct our electronic Fermi surface, and we'll get an electronic charge density wave. As we continue to increase the strength of the translational symmetry breaking order parameter, we will eventually gap out this electron Fermi surface. So then we'll start to get a charge gap. So what you can see here is that these things are not at the same point, right? The charge density wave order parameter is not growing from the same critical point that the gap is growing. So I summarize this on this slide. It's a popular approach, but there is no simultaneous disappearance of electronic Fermi surface in development of translational symmetry breaking. Great. So we really want to understand how we could possibly have these things coincide. And why might we do this? So I'm going to just kind of wink at experimental motivation here. So there's been some recent experiments, really good stuff coming from Wigner-Mott's group. They've been working in moiré bilayer transition metal dichalcogenides. And at 1/2 filling, so that's the kind of, if you subscribe to Senthal's fractionalized theory, that's the kind of transition that you might expect to see here. And what they see is a scaling collapse of electrical resistivity, and they see continuously vanishing charge depth with some critical exponent. So those are the kind of things we're looking for, but this is at 1/2 filling, so there's no translational symmetry breaking. What about fractional fillings? So this is a figure from one of Phai's papers, and I just want to draw your attention here to the 1/3 fractional filling and charge. So that's 1/6 and electrons. And they're able to see an insulator here. So that's that blue area. And the group at Berkeley took a look using STM in real space. What do these things kind of look like? And if I zoom in here at filling 1, so that's 1 charge for every site, there's this triangular lattice. And then if you take a look at this cartoon here, you see the emergence of this √3 by √3 Wigner-Mott state. So this kind of Mott insulating state with this translational symmetry breaking order. However, there's no published results on any transition yet. So
hi, Seth, can I ask a question?
Yeah, sure.
Yeah. So to get the √3 by √3 that's observed, you don't need Mott, right? You just need long range interaction. So you just need Wigner, you don't need Mott for √3 by √3.
Right. So yeah.
So why do we want to insist on Mott there?
That's a good question. Yeah, I think my motivation here, or our motivation, is kind of theory driven, because one thing you could have, as I said, this type of weak coupling thing, you could have maybe an intermediate phase where you have a charge density wave, and then you eventually gap out your electrons, and you have this sort of long range ordered state, maybe driven by like nearest neighbor Coulomb repulsion.
Well, it would be a long range order. Long range Coulomb repulsion, because to get charge order, you need long range piece. But to observe a gapped incompressible state, you don't need the Fermi surface to disappear, right?
To observe a gapped incompressible state.
Yeah, the charge density waves are incompressible and they have gaps.
Yeah, so I think we're ultimately interested.
So I understand this is what you want to study. And,
right, sure.
This is very interesting and I want to listen and learn. I was just asking about the motivation and connections to experiment.
Yeah, so I think
how much of what we are studying here is ultimately minimally required by experiment, and you can ask further questions, but I was just kind of curious, what in your mind are kind of hard boundaries from experiment, and I wanted to make sure that we agree on that.
Yeah, I think we do agree. The transition that we're proposing is exotic, and we might hope that we'll propose some experimental signatures. So maybe it'll be actually what's observed. But yeah, certainly you could in principle explain this with a charge density wave kind of order.
Actually, if I may just add, regarding, maybe I missed the question, but there is an underlying lattice here. So when we talk of a Wigner-Mott, it's just a statement that, yes, you have the long range part of the Coulomb interaction driving this into a crystal, but it is commensurate with the underlying lattice. So there's no sharp distinction when you have a lattice.
Yes, you're commensurate with the lattice, but when you have partial filling and you have long range interaction, so that the electrons have to never really come on top of each other to see each other, how much of a role the U is playing, which is driving the Mott physics?
No.
So you can also bandwidth tune via the next nearest neighbor kind of hopping.
Yeah, the U part, it's just like a cartoon. It's not like you're imagining tuning U. It is just changing the bandwidth. Interaction scales remain fixed, whatever they are.
Right. So I guess but maybe maybe I should just let you talk. But what I was mostly questioning is the observation of a gapped state and charge order at 1/3 does not require Fermi surface to disappear, as far as I can tell. So that's all I wanted to say, because trying to get rid of Fermi surface is I imagine a big part of, interesting theoretical development. But to me, it does not look like that is absolutely necessary. Maybe it is happening, and that would be really interesting to observe.
I'm sorry, actually, now I'm confused. I think the experiment at 1/3 filling shows it's actually an electronic insulator. There is no remnant Fermi surface.
I don't think the Fermi surface is measured.
No, I mean, in
It's just showing
STM,
an
it would have showed
incompressible
up.
state. What you're looking at the data is compressibility.
But there
It's
is
showing that
transport
it's an
data as well.
incompressible state.
No, wait.
It's not
There
a
is-
transport measurement, right?
No, this particular data, but there exists transport data at the same filling in different devices.
Also,
Okay.
if there's a remnant Fermi surface, that would be compressible, right?
No, charge density waves are incompressible. You
No,
just
but
have
if there-
portions of Fermi surface. If you start from Fermi surface,
Right, but there could be a charge density wave that gap out the entire Fermi surface. That
no, you cannot do that with a charge density wave.
Right, so if you have a remnant Fermi surface, it would be compressible.
yeah, I could.
No,
so
it will not. No, charge density waves are not compressible.
No, a metallic charge density wave is compressible.
Right, but
Here, yeah, just
I mean, you have gap and you have incompressibility. All these charge order states are incompressible, and that does not require Fermi surface to disappear.
No, if you have a lattice, and if you have a truly incompressible charge density wave, meaning the compressibility is just, it's incompressible, then that already indicates that you cannot have any remnant Fermi surfaces.
I'm not sure about that. Maybe we should discuss that offline.
sorry, Seth, but I don't want to drag this. But could you go back one slide and just want to quickly confirm one thing? Oh, sorry, maybe just the phase diagram. Decoupling. Yeah. So I guess right now, your main objection, or maybe your goal, is to eliminate the coexistence of a metallic charge density wave.
Yeah.
But so far there is nothing really against this, like from experiment, right? Just to make sure.
So I don't want to discuss unpublished stuff.
Okay.
But possibly, yeah. I mean, I'll let Debanjan.
I mean, no. What Chaming is saying is absolutely true. I'm not aware of any experiment that would rule out the intermediate phase.
Yeah, and going across the star thing may cause some kink in compressibility, but it would not make it incompressible. I mean, from one side to another. So if I were to really just, if I'm a big fan of a recoupling theory, I would make the gray star yellow, maybe, if you wish. But okay, that's I just want to make sure that is not yet a thing that is so
rolled out.
Yeah.
I would say that. Yeah. Sorry, Debanjan.
No, I was just, what was the comment about yellow versus gray? I missed that.
Oh, I was saying that if we want a metal insulator transition, a nice and weight coupling yellow metal insulator transition, I may want to highlight the green, like the gray star. That would be the simplest metal insulator transition. That's basically
right.
Chemical potential.
Yeah, that's a Lifshitz transition, the gray one.
That's a Lifshitz transition.
Yeah.
Right.
Yeah, it's gray for being somewhat boring, I guess.
Right. Okay.
Yeah, I assume that came through.
Right. Okay.
Yeah. Okay. So this is the kind of weak coupling, and I waving my hand here at some of these experimental motivations. But let's hop right in to some of the theory details. So I just want to review this metal insulator transition at half electron filling. This is from Senthil's paper in 2008. Okay, so what we're doing again is we're just going to formally write down the electron operator as the product of this charge on and the spin on. And what we find is that we have this extra U1 degree of freedom. So if we multiply the charge on by the space factor and the spin-on by its conjugate, then we will leave the physical electronic degree of freedom unchanged. And in order to deal with this, we find that we get this emergent U1 gauge field A. So A is going to, in any sensible system, in any system where your electrons are your true degrees of freedom, the A is confining. The A binds the charge on and the spin on together. So the main idea then is that we can think of the metal as a superfluid of the charge-ons, which means this expectation value is non-zero. And the electron then is just kind of, for most intents and purposes, just a dressed spin-on. So B is acting a little bit like quasi-particle residue, just measuring the overlap with the electrons. As we move on to the Mott insulating side, now the expectation value of B will be 0. And so this spin-on Fermi surface, it no longer has any overlap with an electron Fermi surface. And so what you can see here is that this is really, as I suggested, maybe just a superfluid to Mott insulator transition of the charge-ons. But we see this extra A term here. We have to be careful with that. And there are additional couplings. So throw a bunch of equations up here, but this is just the simplest theory you could write down, which couples this dynamical emergent gauge field minimally. So it couples to the spin-ons, it has dynamics, and it also couples to the charge-ons here minimally. So the charge-ons at filling 1, they have this particle hole symmetry, and so you write down this relativistic theory for them that looks 3D XY like. And finally, you also want to include some kind of couplings of the charge-ons and the spin-ons. So those take the form of these energy-energy couplings, like B squared F dagger F, for example. So this is the field theory that we want to work with. And it turns out that this extra coupling, SBF, and the coupling to A mu are not going to turn out to be relevant. And I'll walk through those arguments. So really, all this criticality boils down to a 3D XY transition of the charge-ons, superfluid to insulator. Great, so let's talk about the irrelevance of the emergent gauge field A. If you do some kind of analysis where you integrate out the spin-ons with a diagram like this, you'll pick up this Landau damping term, which I've just written here. The important thing is just that we have this omega over a q, and we know that the charge-ons are relativistic, which means that omega will scale like q, z equals 1 in the charge-on sector. And so this Landau damping term is just going to act like a Higgs mass in the charge-on sector, and we can neglect the A mu field at the critical point. We can also look at the energy-energy coupling and just do some power counting. So we know that energy scales like d minus 1 over nu, where this is not a filling anymore. This is a critical exponent. And so we see this energy-energy term is going to scale like 2 over nu minus d. And that means as long as nu is greater than 2/3, it's irrelevant. But in the 3D XY transition, nu is greater than 2/3, and so that's irrelevant. So just a quick review. The couplings from A mu and these energy-energy terms are irrelevant at the critical point, and the transition really is just driven by this 3D XY superfluid Mott insulator transition. So that's the picture at 1/2. Well, what can go wrong when we have translational symmetry breaking? So as I said before, we have these couplings now. We have this charge density wave order, √3 by √3 in this picture, that can couple to the spin-ons. And we can imagine coupling the gauge invariant F dagger F to these order parameters rho q, which is charge density wave at vector q, and n, which is this pneumatic order parameter. And if we integrate out the spinons, we're going to get the same kind of Landau damped terms. So we have the standard Landau damping term for the pneumatic order parameter. And for the charge order parameter, we don't have a q here because it's been cut off by this big q with the charge density wave. So this is our effective field theory for these kinds of order parameters without knowing anything about what the charge on criticality looks like. At the end of the day, these parameters, since the CDW, the translational symmetry breaking, is showing up in the charge on sector, we'll see that these parameters are in fact described by chargonic degrees of freedom, but we haven't really investigated anything. We've just thought about coupling to spinons. So if we just do power counting again, it tells us that in order for these terms to be irrelevant, we need the anomalous critical dimension of the CDW order parameter to be greater than 1, and the anomalous critical dimension of the pneumatic order parameter to be greater than 2. And the same arguments for the irrelevance of A mu and energy-energy couplings will go through in this setting. So we still need z equals to 1 in the charge on sector, and we still need nu greater than 2/3. So these are all the things we need to make sure these additional couplings don't spoil this kind of coincident transition. How do we actually treat this charge on theory for fractional fillings? So now I'm going to be working off of this great paper by Burkov and Valence. They decided to use the particle-vortex duality, which makes writing down a chargonic theory at fractional fillings much easier. So I'm going to kind of wave my hands at some of the details here. But the idea is that instead of working with the charge-ons, these bosons in blue, we want to go to the vortices. So there's some chargonic superfluid, and we want to look at the vortex of that superfluid and make that our new degree of freedom. So the condensate of the charge-ons has gap vortices. It costs energy to create these swirling superfluid vortices. And the chargonic insulator is going to have condensed vortices. And it will turn out to be easier to deal with fractional fillings by going to the vortex dual. And why is that? Well, it turns out that when you have a vortex which lives at the center of the triangular lattice plaquette, and so it lives at the sites of this dual hexagonal lattice. If you take a vortex around a boson, this charge-on, it will acquire a phase. And so if you're in a fractional filling where you have some fractional expectation for your charge-ons on each site, you're going to pick up a phase that is not equal to 1, a non-trivial phase. So in the 1/3 case, that's e to the 2 pi I over 3. And that means that if you decide to move a vortex around in a circle, you're going to need some different flavors of vortices because the vortex isn't going to just return to itself under these fractional phases. So we need this vortex multiplet, whatever it is, to transform amongst itself under lattice symmetry operations. So if we do this kind of circuit, we might take vortex flavor 0 to vortex flavor 1 to 2, and once we've done it 3 times, we get back. So Burkov and Valence worked this out, but in terms of our phi, our vortex degrees of freedom that we're writing down here, this is what all of these symmetries do to them. And I pictured the symmetries here. So we have translation by unit vector 1, 2, reflection by D1 and D2, and then rotation about this purple site. Great. So once we've set out to do fractional filling with vortices, we have this projective symmetry group, which just describes how the real space operations transform the flavors of vortices. And we know that the full theory must respect the projective symmetry group. I just want to give a little aside here to give some physical intuition as to like what these phi L's are. If we condense only a single one of these vortices, then vortices of the vortices will correspond to a physical charge on. So that allows us to kind of go back to the charge-onic picture. If we condense all three of these, then if you create a vortex, it's going to correspond to a third of a charge-on. So the charge-on has kind of fractionalized due to this fractional filling if we're viewing it with these vortex degrees of freedom.
Hi, Seth.
Yeah,
Before
sure.
you go on, yeah, I want to ask, so you put in this ID1 and ID2, these are reflection symmetries, are they?
Yes, yeah.
I see. So, but the actual TMD material probably at best only have one of these, or you may want to think about other. So I'm just wondering, you know, how you think about this reflection symmetry.
Yeah. So I think that when you write down the theory here, so let me just skip ahead to the theory. So when you write this theory down, you'll have these two quartic terms.
Yeah.
And I don't think both of these reflection symmetries are necessary to get only these two quartic terms. Like I think you would at most need only one of them. And everything we say today just comes from this theory here. So we're, you know, if you go to sixth order, for example, losing one of the reflection symmetries may make your sixth order terms more complicated. But we just need the quartic terms.
I see, but I just want to make sure. So here we're just saying that, let's say hypothetically there are these these two reflection symmetry. We haven't gone to the details of how it connects to the actual TMD stuff, right? Just to make sure.
Yeah, right. So what I'm saying, I have not checked removing one of them, but I think, you know, a long time back when I was re-deriving valences results, I think you only need at most one of them.
Right, and that one better be the one preserved by the sample, because otherwise it would be more complicated, right?
Yeah.
Okay.
But it's something actually that's easy enough for me to think about and then just email you.
Thank you.
So, yeah, thanks for the question. Great. So we have this projective symmetry group, and we can write down a theory which is consistent with it, and it's this sort of large theory here. So let me just point out some symmetries of this theory. We have our vortex degrees of freedom, and as you can see, the translational symmetry kind of permutes these vortex degrees of freedom, and it turns out that there's, you know, you have full permutation, not just cyclic permutations, and so you have full permutation symmetry of your vortex multiplets. You also have this non-compact U1 gauge field, capital A mu. That complication is really just there because you're picking up a phase when you take a vortex around a boson, and this gauge field is accounting for the phase that you pick up. So that's why that appears. And then finally, you have particle hole, because these are vortices. So clockwise versus counterclockwise is particle versus hole, or hole versus particle. And the theory makes no distinction between those. So we have this particle hole symmetry. So this is the theory at 1/3. And Birkhoff and valence look at what happens at mean field for this type of theory at 1/3. So if G is less than 0 at 1/3, this is this quartic term G. G is less than 0. We condense only a single vortex flavor, And so at the critical point, there's, if you condense only a single one, there's no splitting of the charge on, no E/3 particles. And it turns out that the charge density wave associated with this G less than 0, only a single one condensed, is of the √3 by √3 type. Now, if G is greater than 0, you condense all flavors and you get CDW, you get these Wigner-Mott states, which are of this form. So either this stripy kind of thing or this triangular superlattice. Yeah, so this is the mean field, but as you can see, this is a very complicated field theory, and it's hard to deal with. It would be even harder to understand whether or not the charge density wave and pneumatic order parameters are relevant. So how do we deal with this strongly coupled theory? Well, we're just going to extend it. We're going to extend it, and we're going to try to take it to some sort of calculable limit. So we take each vortex flavor and we promote it to this complex vector in Cn. And we'll require that the action have this extended SUN symmetry where we act on all of the vortex flavors with U in SUN. And that gives us this theory here. So it's the same type of theory as you can see, and we've just promoted the phi's to vectors in Cn. And we've also arranged for this n counting for a mu. This will allow us to eliminate a mu as we take n to infinity. So this is, if you're unfamiliar with something like this, this is done commonly in like CPN-1 models. And you can find a lot of textbook treatments of it. So, all right, in the n goes to infinity limit, a mu will drop out, and this will just become an O2n to the third product with S3. So what that means is just all of these vortex flavors are permuting amongst themselves, and each of them individually has an O2n symmetry. Now, thankfully, this was already, it saved me a little bit of work. This was already studied by Osborne and Sturgio. In the high energy context, they used a 4-epsilon expansion to find a stable fixed point at lambda equals 0, G greater than 0. And that means this, so this lambda coupling is 0 at our fixed point as n goes to infinity. But you can see that the only way that these vortex flavors are coupled, apart from this non-compact U1 gauge field that's dropping out, is in fact this lambda term. And so the critical point is actually 3 decoupled O2n models with each of these vortex flavors decoupled.
Hi, Seth.
Yeah, sure.
So this is large N, and you also have to do 4-epsilon, or that's just the easy way to think about it?
That's just an easy way to think. So Sturgio also did some bootstrap as well for this type of transition. I think, yeah, so it may actually be necessary to do the 4-epsilon.
Oh, you're saying I cannot just take the theory in 6 and do pure large N in 3 dimension, or maybe it's more complicated that way, and maybe there's some parameter space not fully explored.
Yeah. So there's when Osborne and Sturgio were doing this, they were looking at sort of generic forms of quartic couplings, and I think there's some subtlety with making sure that you don't flow away from an ON to the third S3 model. But yeah, I should check that.
Are you saying you cannot just take the saddle point theory of n to n equals infinity and look at 1/n corrections?
Yeah, so right. So one thing that we're doing here is for us, it's critical that this a mu drops out because we want to look at this O2n to the third cross with S3 model. And for that, a mu has to fully drop out. The theory with a mu included in the large n limit hasn't been studied. And so in order that a mu fully drops out, we're looking truly at the n equals to infinity limit here. So we haven't characterized.
You're going to look at the n equals to infinity, the saddle point.
Yeah.
And this 4 minus epsilon expansion, they probably worked without large n limit. Did they also? Well, I don't understand.
Right. Yes, you're right. They
do one or
without,
the other. You don't do both.
Yeah. They did work without the large n limit. But right. The point I'm trying to make is that our theories are not the same unless you go to the large n limit, because our theory has this non-compact a mu, whereas they truly are just working with the O2n to the third.
I mean, yeah, I would imagine the two theories are different with different fixed points, because one is doing epsilon expansion and the other is doing large n. They are often different, right?
Yeah, so one thing that we were studying is looking at the large n theory, adding back in some of these a mu corrections and determining their relevance.
And is that the same thing as looking at 1 over n corrections, or is it different?
Yeah, so what our 1 over n corrections, you have some corrections that are coming from your O2n theory, and you have some 1 over n corrections that are coming from your a mu coupling.
Okay, well, maybe we should just let you do it.
Yeah, so for what we're considering, we're really just looking at this proof of principle, whether or not we can show that these couplings are irrelevant. And so we didn't compute 1 over n corrections, but in principle, it's something that we could do.
You're interested in irrelevance of couplings so that you have a continuous transition?
Yeah, correct. Yeah, so we just want to see in the extremely large n, do we flow to a place where we can have charge density wave occurring at the same critical point that you get a Mott insulator.
I see. So the goal is to see what would it take to have a continuous transition.
Yeah, that's correct.
Central head at 1/2.
Exactly.
Now with 1/3 and simultaneously breaking translational symmetry.
Right. So yeah, when
the goal is really, what's really important to you here is the continuous transition.
Yeah, that's exactly right. Yeah.
Okay.
So right, when I talk about extensions at the end, one super important extension is that we're really just looking at the extreme n limit of this theory, not even characterizing 1 over n corrections. And so it would be important if we want to actually describe the experiment to look at the n equals to 1 limit, or even like reasonable values of n.
That sounds very ambitious. Not sure if that's possible.
Well, yes. There's a reason
we
why.
can have dreams. We can have dreams.
Yeah. So as a proof of principle, with this large n extension, we see that we'll achieve the irrelevance of little a mu, this emergent U1 gauge field, because we have this relativistic theory for vortices. So z equals 1 in this sector. And we're also going to have nu greater than 2/3. And that's coming from just the fact we flow in the n equals to infinity limit to these 3 decoupled O2n models, and those have nu equals to 1. As for the anomalous dimension of the CDW and the nematic order parameters, we need to work that out. So again, I'm not showing the details here, but you can construct CDW order parameters out of bilinears of vortex multiplets. So when you combine these vortex multiplets with some phase factors, some linear combination, you can do this and show that your order parameters obey the correct transformations under translation, rotation, reflection, as you would expect from an order parameter. So that allows us to connect this chargonic theory, this large N theory, to order parameters for CDW. The most important order parameters probably are the ones for the mean field CDWs when G is greater than 0, because that's the fixed point we flow to in the n equals infinity limit. And those are the order parameters corresponding to these kinds of CDWs. But unfortunately, as you can see in our paper, it turns out that at this O2n decoupled fixed point, the anomalous critical dimension is 1, and that means that these are marginal. So again, continuing in this vein of a proof of principle, we consider a Fermi surface which just avoids hotspots of these vectors. So rather than dealing with marginality, so say that we take this Fermi surface. If you translate it by this wave vector, which corresponds to a kind of stripe ordering for G greater than 0, we can avoid hotspots. And in fact, you avoid hotspots with this Fermi surface for all of the CDWs that you expect to get for G greater than 0. But unfortunately, this Fermi surface is nearly nested at the √3 ordering that we don't flow to. But thankfully, that particular ordering has an anomalous critical dimension of 3. And that's greater than 1, so this type of coupling is irrelevant. So we're able to dispatch with these kinds of CDW couplings. And I don't have a good picture for Dynamical.
Wait. Well, one more question. So
Sure.
your G larger than 0 patterns, which you now have in this picture,
are not what's seen in an experiment?
No, not even before not seen in experiment. This will not be favored by further
Repulsion.
Repulsion, yeah, you wouldn't do that, right? So why do you consider this?
So in our large N extension, this is the type we flow to these G greater than 0 fixed points. Yeah. So that's why we consider it. Whether or not it's physically relevant, probably not. We were trying to perhaps cook up some explanation for, so if we consider this super lattice site, but perhaps there's some sort of super exchange that's going on that lowers the energy of this state, but we weren't able to come up with.
So I guess an interesting question is, your theory is purely, effective theory. So you don't have microscopics. Your theory at the moment does not know there is Coulomb repulsion, which will make this not happen, right? So it's so Coulomb repulsion would have to do something to your effective theory to not let the RG flow to this unphysical, under the physical laws, fixed point. So that would be interesting to find out.
Right.
In my biased mind.
Yeah, I think that's a great point. At half filling, that the 3D XY, there you really are just working from a Bose-Hubbard model where you do have some kind of like on-site repulsion. But you're right that our model, this next nearest repulsion is probably not there in the microscopics.
And your model saying this is a stable fixed point is clearly ignorant of nearest neighbor repulsion.
Right.
Stronger, right? So that would have to do something in your low energy effective theory that would.
Yeah, I agree.
Charge,
yeah.
Right? So it'd be interesting to figure out what that is.
Yes, definitely. Yeah, I agree with all of those points.
Seth, before you go on, sorry to keep asking questions. So this is probably a technical thing, but is it impossible to avoid hotspots if you have only one Fermi pocket?
Is it impossible to avoid? So at 1/6 filling, you would have to make it extremely weird. So what effectively these two pockets do is they allow us to shrink this central thing.
Yeah,
so that when
that's right.
Yeah. So I tried to search to see if I could avoid all hotspots, and that's not really possible. So you always end up having a hotspot either with the G greater than 0 or the G less than 0. Thankfully, G less than 0 for our theory doesn't tend to be important. But I never saw anything where you have a single pocket and you're avoiding.
I see. I think for half filling, you can probably make a rigorous proof. I suspect that maybe.
Yeah, half filling is big enough.
Yeah, it's basically that multiple copy would have to tile up the entire thing, and you also want them to avoid themselves. That's really impossible unless they come in funny shapes. So. Yes.
Yeah, I mean, you would probably need to, if you would want to get this to work, so your vectors are like this vector here, this vector here. Right. And I think if you just avoid those, so maybe you could try to bulge away from that and into these diagonals, but it would be weird. It would be a weird Fermi surface.
All right.
Yeah, so the nematic order parameter, you can just prove formally that if translation invariance is preserved, you take that projective symmetry group, then any rotation symmetry breaking order parameter has to be at least quartic. So that means that the anomalous critical dimension is greater than 2. So that is also irrelevant in this large N theory. So all of these couplings are relevant, and I'll just review what I'm saying here. So you can see the various approximations that we've made. First, we've promoted each vortex flavor to an N vector. And we avoid hotspots with this kind of odd Fermi surface. And we also flow to a kind of interesting Mott insulator for the charge-ons in real space. So we do all of these things that are kind of weird, but nonetheless, we achieve a theory which is a metal, and immediately when you transition into the Mott insulator, you develop a charge gap, you develop CDW order at the same place, and you don't spoil the criticality of the charge-ons. And so this type of theory is in fact possible, albeit probably not physically what's happening. But we can make some predictions as long as the criticality of the charge-ons is not spoiled. We can make predictions for experiment. It doesn't have to be of this specific weird form. But so here's just some predictions for experiment if you have this coincidence of the charge density wave order parameter and the charge gap. So if you have this kind of fractionalized transition, you can expect an effective mass which diverges logarithmically. That should show up in the scaling of the t-squared resistivity and the Sommerfeld coefficient of the specific heat. The quasi-particle residue should vanish as you go from the metal to the insulator. In our theory, it vanishes with exponent 1, which is 2 beta. And finally, the compressibility should vanish upon approaching from the metallic side. So all of these things that you would also see at half filling, you should see at fractional fillings as well. But the critical exponents may be different than half filling. Now, what's the difference? So unlike the metal insulator transition at half filling, we now have translational symmetry breaking order parameters. And those will have some those will have some scaling. So in our large N theory, everything but the root 3 order had scaling dimension 1, and the root 3 order had scaling dimension 2. Finally, we get an enhanced jump in critical resistivity, this universal jump. So this is actually Xiaoming and collaborators have a good paper on this, where they go over many other ways that you could fractionalize and consider this enhanced jump. So just as a quick review of this universal jump, when you have this fractionalized theory, you can show that your resistivity is just a sum of the resistivity of the charge-ons and spin-ons. Now the charge-ons on their superfluid side, this is 0. And on the insulating side, it's infinity. But right at the critical point, it has some critical value. And so there's this universal jump, which is driven by the critical value of the charge-on resistivity. And for 1/2, that's h/e². But if you fractionalize your carriers, if you condense all your vortex flavors and you have these e/3 particles, then their resistivities will add in parallel because any of them can carry the current. And so your total resistivity will be enhanced by a factor of 3 due to this fractionalization. So summary, adding translational symmetry breaking to the fractionalized metal insulator transition is tricky. We did this large N generalization to show that all these extra couplings aren't relevant, and you can in fact have this kind of critical point that I showed at the beginning. Many of the same experimental predictions will go through. Going forward, so what about the n=1 theory? Do we actually get this root 3 by root 3 ordering? Is kind of, as Una was pointing out, these unphysical states, is that possibly because of the large N extension, or is there something more fundamental that needs to be added to this theory? Can we do away with the spin-on Fermi surface? So at the same time that we gap out the electronic degrees of freedom, we still have the opportunity for a theory to be a thermal conductor. So the spin-ons can still carry heat. And it might be interesting to study this theory when we gap out the spin-ons at the same critical point as well. So a lot going on at the critical point. And Debanjan has a great paper with Lujan at 1/2 that can do that. So perhaps maybe extending that. And then finally, what happens if we dope? So just add slightly away from 1/6 electron filling. Do we spoil this transition? And finally, I just want to close out. Thank you, everyone, for hosting me a month ago. Thanks to Spinful, thanks to Debanjan and the NSF. And most importantly, thanks to everyone for listening and for your questions. All right, any other questions?
Just set the hand. Yeah,
Could you
any other
please go
questions?
back to the second page of your prediction?
Sure.
Yeah, 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 this one. So the second statement, what are the ways to test it?
So possibly STM, if you're able to image the charge, possibly imaging the strength of that.
Well, I mean, that won't give you delta rho. You have to measure the structure factor, which I don't know how to do in TMD setups.
So some kind of a diffraction?
Possibly.
Yeah, I think the most critical thing to establish is whether or not you get these charge order exactly at the critical point. If you know, it's possible that you have something like the weak coupling, where you move this charge ordering over to the left here, and you have some intermediate charge density wave metal. So you could measure the scaling at that point. But the more interesting thing may be to see whether or not those coincide.
Within some experimental resolution. I mean, you can never really say it's exactly.
Yeah, right.
But the existing STM observation of the Berkeley group is √3 by √3, right? And
yes, that's correct. Yeah.
If you think about the Coulomb repulsion, you wouldn't think anything else. So
yeah. I certainly agree with that. I don't think what the Berkeley group, what would be nice to see is whether or not you could have some establish that you're getting this charge density wave, the √3 by √3 one at the same time that you're becoming an insulator.
So can I flip your prediction to say that √3 by √3 cannot happen through a single continuous transition?
No, I don't think so. I mean, it's possible that, you know, the strongly coupled theory that we wrote down, maybe there's some kind of additional thing that one could add, but maybe the n=1 theory just gives you √3 by √3. Yeah, so we haven't proven that anything's impossible. We've just shown that it's possible within some sort.
What you've shown to be possible is not what's been observed, right?
Yeah, that's correct.
That's kind of little inconvenient.
Yeah, I would agree.
Yeah.
A quick question. So maybe this is already a measure, or if it is, please remind me of that. So when people observe this √3 thing, the magnetic susceptibility has no singularity whatsoever going across such a transition, or is that right? Or is that been measured before?
It hasn't been measured yet.
Oh, it hasn't been, because all these type of theory, let alone what happened to the charge, like the naive version of it has no, basically the magnetic susceptibility doesn't see anything. That would be a pretty,
right.
Okay, I'm not saying like what theory is correct, but like this fractionalized stuff seem to all have this kind of a feature.
Mm-hmm.
But very plain charge order also wouldn't show anything in magnetic susceptibility.
Sorry?
Yeah.
Just plain, simple charge order.
Right, but going from a metal.
Susceptibility.
My point is going from a metal to a simply charge density wave thing would have a strong signal at the transition. Not
in spin susceptibility, not magnetic susceptibility.
Why is that not in?
Because it's a charge order. Has nothing to do with spin.
Right, but afterwards it becomes a pure insulator, so everything is gapped.
Yeah.
Well, yeah.
So
well,
if the load
that's somewhere, yeah. I mean that's somewhere deep down, in the I don't know small t limit, I guess.
No. The point
in the
is,
zero t limit, you can study the insulating state in the limit of absolutely 0 t.
Sure.
You just get a nice √3 by √3 with your double gated potential.
Yeah, that's fair.
And that does not require anything magnetic.
That is absolutely true.
That's not the question. The point is in that t=0 limit, the metal has a standard metallic susceptibility, so chi independent of t because of the electronic Fermi
zero limit. You don't have metal because it's T0.
Yeah. So base temperature 300 milli-K, phi and G have measurements that it shows you it's a T independent susceptibility. Then if that susceptibility evolves smoothly into a Wigner crystal, without the spin susceptibility dropping down, that means that the spins are still, there are lots of low energy spinful excitations. Because even in the charge ordered state, the electron still has a spin. It has to do something.
Right. So yeah, let me go back to the weak.
So you're saying if this was just charged thing with nothing spin, nothing quantum, then you should see a classical like paramagnet.
Exactly.
Mm-hmm.
Exactly.
Yeah, I agree with that.
Yeah.
You're saying that's not what is observed.
No. We don't know what's observed because that measurement for this fractional filling hasn't been done yet. Or maybe it has been done, but we don't know about it.
Not to your knowledge at the moment.
Yeah,
at
so
this
for
minute.
example, that's right. For example, if we come back to here, if we would talk about this gray star transition, then magnetic susceptibility would see that.
Right. Yeah, because what you're doing is, since you have the spins, you are having this charge density wave, which is √3 by √3.
Mm-hmm.
But you also, I mean, the spins will do something. So at t equals to 0, if you had this kind of super triangular lattice, you would expect a 120-degree nail state.
Mm-hmm.
And so if you do that, then you're going to freeze out the spins.
Yeah, I agree. Yeah, that right.
So I have something very naive, maybe very stupid. So if we go back to the final conclusion, that phase diagram, right? I just want to make sure I read this correctly. So you predict that Mott transition and the Wigner transition for fractional filling, they should occur at the same point, that red star.
I would be I would be most interested if they do.
I think it's not a prediction. I think it's if that is to happen, if that is what's happening, how would you understand the theory underneath such a transition? That's the question that these people answered.
Yeah.
So that's a condition going in. It's not a prediction.
Yeah. I think if they are not coincident, so if you have an intervening like CDW metal,
or then, if it is first order,
or if it is first order, then there's less as a theorist that one could say about that, probably.
At least this theory cannot say, because this theory was specifically for the case of a single transition that's continuous, right?
Yeah.
Very interesting, though. It's a very interesting theory, I must say.
So I think we shouldn't worry about the first order because I think there is data that rule that out, but it could still be a two-stage transition, and that's something we don't know yet.
Yeah.
I don't know. I maybe I'm not following the data as closely as you guys. Last I checked, the gap was changing more abruptly than in half filling. One-third is very different from one-half.
But there is no hysteresis. And there's no hysteresis.
But it is a discontinuous. The gap didn't seem to be closing continuously. Unlike half-filling data. Half-filling data is continuous and there is all the scaling. But one-third didn't have that.
I don't think the gap changes discontinuously. I mean, I don't know if Benjamin is here or if we should be talking about the unpublished data yet, but it just, the functional form is different, but I don't think it like jumps or anything.
G, can you tell us? Maybe not.
Yeah, so I think that based on the current measurements, gap closes continuously. But I doubt, they will occur at the same point, the red star. But of course, this needs to be checked more carefully.
Wait. You're saying the charge gap and something else are not happening at the same point?
No, I'm trying to read this.
Yeah. You said you doubted whether or not they would.
I want to make sure that I read this picture correctly. So the black is for Mott transition, right? At touch filling 1, and then the blue.
No. They are
Sorry.
saying there is a transition associated with disappearance of Fermi surface and development of charge order occurring simultaneously in the fractional filling sample.
So G, if I may just elaborate. So basically, let's say you're studying the bandwidth tuned transition at this 1/3 charge filling. Then let's say you measure delta, the gap from exponentially activated transport in the insulating side. So you see where that charge gap vanishes, at what value of the electric field that charge gap vanishes from transport at the 1/3 filling. And I don't know how you would do this, but imagine if you could measure where the charge density wave order parameter is also vanishing as a function of the displacement field. What this theory is trying to describe is the situation where they both vanish at the same critical point.
Okay,
rather
good.
than
Gotcha.
Yeah.
Right.
That's right.
I was confused because you called this Mott. Okay.
It's
fine.
Wigner-Mott. Yeah, sorry. Kind of abused language there a little bit.
Okay, so that makes more sense now. Okay.
Right, and I guess the real measurement, as I guess we have discussed,
We cannot answer the
previously.
second question yet.
Right, because I think the thing to measure would be measuring Hall and something like susceptibility over the same extent of displacement fields to see if there's an intermediate.
The change in the Fermi surface.
Right, to see if there's an intermediate metallic phase, perhaps, which is reconstructed.
Thank you.
All right, well, other questions? Well, we had quite a few, so.
Thank you, Seth. It was good to see you. Thank you for
it was good to see you too.
very interesting work.
Thank you.
All right, well.
Thank you.
So yeah, let's thank Seth one more time, and we will reconvene again in the new year. So happy holidays, everyone. Have a great start to the new year.
Holiday.
All right. Bye-bye.